Hello, everyone. My name is Dave Beckberger. I am a senior graph architect on the Amazon Neptune service team. And I'm here today to talk to you a little bit about graph databases, and then to kind of go into a little bit of a deep dive and a demo on Amazon Neptune, which is AWS's purpose-built graph database offering. So let's jump right into it. So today, when we work with customers, we see graphs being used for all types of applications. Why is this? Because graphs are very good at modeling relationships that are not necessarily easily represented or retrieved with other types of databases out there today. If we look at this simple graph representation, it's pretty easy without me having to tell you any other additional information that you can figure out that Alice lives in any town and that she works with Bob. This is because this represents how graphs and graph's way of looking at problems is very intuitive to people, because it does a very good job of representing the natural way that we think about data and connections. And in this example, we're looking at these and we have what we would consider from a graph perspective a couple of nodes, those nodes representing the entities or the real world objects here, in this case being Alice, Bob, and Anytown. And we have these lines or these connections between things which represent the relationships between these real world objects, in this case lives in and works with. And when we look at this, and because of the way that graphs and graph databases store this data, they really allow you to explore these relationships and patterns and this type of connected data in ways that other data stores and data structures can't. Customers are also very excited about graphs, and they're really especially excited about managed graph services. Since Neptune was released in May of 2018, customers have built many types of applications on top of Neptune. But when we think about it, when we're working with customers, we kind of broadly generalize these applications into a couple of common use cases we see. The first common use case we see with Neptune is fraud detection. And this is exactly what you think it is. We're trying to use graphs to help find the bad guys. Graphs are uniquely helpful for fraud detection, as they really enable us as developers and as users of the system to find the deep links and deep connections and patterns of connections in the data that really aren't easily found using other sorts of systems out there. The second use case we generally see is what we call identity graphs. And identity graphs are really based on the concept of something like a user is going to come to your website from multiple different areas. Maybe they are going to connect to it from their phone and their work computer and their home computer and their tablet. And we really want to be able to connect these disparate interactions with the user together in such a way that we can kind of generate a golden record, or kind of the canonical form of that data that a user can actually so we can actually use that to help provide things like personalized recommendations or marketing ad segmentation, things like that. Third use case we often see with customers are one of knowledge graphs or knowledge organizations. And this is really about connecting disparate data silos inside of a company together in such a way that you can really get a holistic view of a specific of pieces of information and things that are connected to that piece of information. Let's say you're something like an e-commerce website and you have a database that contains all of your information about the products you sell, and one that contains all this information about your customers, and one that contains all the information about your inventory inside your warehouse. Maybe you have another one that's shipping, and you want to be able to connect all of these together in such a way that you can look at all of the information around a specific product or customer or user, something like that. And that would kind of fall into what we call a knowledge graph type use case. The last one we have is the last common use case we've seen is security graphs. And we've recently seen a real uptick in customers interested in using graphs for security-based systems. Security in general is sort of a graph problem, because it's really, security for anything, be it physical or logical or application security or your cloud infrastructure security, is really about layers, about multiple different layers of security all being connected together in such a way that you want to be able to look at that, to be able to find potential paths of potential malfeasance, or paths through the graph, and how things may or may not be exposed to the internet per se when they should or shouldn't be. So that's sort of kind of what one way we can look at security graphs. And This is really kind of a really interesting and fast upcoming segment for graph-based solutions. So what are some other common business problems that you think that we work with customers when we think about graphs and graph type problems really needing those highly connected data? Well, as I kind of mentioned already, the first one is people come to us saying they need to do things like be better at detecting fraud and fraudulent transactions inside their system. Maybe they want their customers to have a better or more personalized recommendation experience than they're able to provide today. There's that knowledge graph use case of we want to connect together those siloed data sources inside our enterprise to really kind of build out an entire platform that contains all of the knowledge inside of our system. Maybe you have those multiple websites or you have multiple applications and you need to link together disparate customer identities in these systems to kind of get that canonical or that golden record, maybe you have machine learning algorithms and you want to be able to use the connections in your data to improve those algorithms to give you better sorts of answers. And these sorts of questions are the ones that kind of are, if you went out and you looked online, you did some searching around, you would probably come back that these sorts of questions are really good common business use cases for graph type problems. But there's also a wide array of not so easily recognized graph problems, ones that when you at first glance may not make sense, or you may not think of them as graph problems, but they really do lend themselves very well to being solved using graphs. First one here, example is, what are the risks in your IT infrastructure, your supply chain? Any sort of IT infrastructure or supply chain, it tends to get very complicated very quickly. There's a lot of, in the case of a supply chain, you have a lot of people that are, you have a lot of products. Each of those products has its own bill of materials. Each of the items in those bill of materials has one or more suppliers, and those suppliers have suppliers, and those suppliers have suppliers have suppliers, and being able to kind of look at the overall risk portfolio of your supply chain or your IT infrastructure is a great use for a graph. Where did this data come from? This sort of question of being able to track the lineage or the provenance of data is one that we often talk with data engineering teams about. These lends itself very well to a graph, because if you can think about it, when you're sort of working with any sort of data engineering problem, it's really about taking data from one source, doing some sort of extract, transformation, and load type process, and usually loading it into something else. Maybe you're combining or aggregating that data, but when you aggregate that data, you still want to be able to track, where did this data come from? Maybe you need to be able to track this to be able to comply with privacy regulations like CCCP or GDPR. And you want to be able to track not only where this data is currently, but where are all the places it was used intermediately to be able to, clean up those things, to be able to understand the accuracy and the efficacy of the data that you're working with. Why don't your search results relate to the specific question was asking? This is a common use case we see with customers, is they have search results, but those search results are a little bit lackluster and a little less clear than they would like them to be. So being able to use a graph to be able to build that, those sorts of knowledge graphs where you're connecting these data together to be able to give you more relevant and related answers to the types of questions people are asking. How does person X have access to information Y? This is another security graph type use case where you really want to be able to, maybe map out the permissions that folders and files have via Active Directory groups. I was working with one customer where their specific use case was they were, they wanted to specifically look for access, or people that had access to certain files and folders through a very, very long set of connections, because if they had if I was given direct access to this file or folder, it probably means I was intended to have it. But if I had to if I had access to this file and folder through multiple sets of groups and permissions, maybe it was an unintended consequence of giving me a permission, was giving me access to this critical business information. And they want to be able to kind of track that down and look for that sort of thing. And, things like about your cloud infrastructure. Your cloud infrastructure is a very good example of a security graph type use cases. Being able to look at how different things are used inside of it through a wide array and a very large number of variably connected data. If you think about your cloud infrastructure, you're going to have things like IAM policies, which are connected to roles, which are then going to be connected to one of any number of different types of entities, be they Lambda functions or databases or EC2 instances. And you have a very variably connected set of entities that you're trying to look at. But when I really kind of sit down, if I wanted to kind of boil down graph questions, the types of questions that graphs are good at answering, really for me, it comes down to the where, why, and how questions. Where are the risks? Where did the data come from? Why don't the search results do something? How about this person? How is this role being used? Things like that. And these tend to be good graph questions because they have a few things in common. First, they tend to navigate variably connected structures of data, especially if you wanted to think about this in terms of looking at your cloud infrastructure. The cloud infrastructure, as we kind of discussed a minute ago, is really, it's a highly variable set of different entities. You have, VPCs, you have ENIs, you have IAM roles, IAM policy. All of these are connected together against other EC2 instances or databases. And being able to look at that and easily move through that sort of information is an area where graphs tend to excel. They also tend to excel at questions where you need to filter or compute a result based on the strength, weight, or quality of a relationship. So in the case of something like a supply chain risk management, being able to look at not only the fact that these two things are connected, but how important is this supplier to this person? What other sorts of backup suppliers may they have for specific things, to be able to use that to help calculate an overall risk of your supply chain, or where the risk, or to find the riskiest parts of your supply chain, is an example where using the connections in your data is extremely important to be able to get that answer. And finally, recursing or requiring traversing unknown numbers of connections. And this is really an area where graphs really do excel. And this is where you have questions that are a bit open-ended. Let's take a look at the example of, how does person X have access to information Y? They may have been given direct access to this information, or they may have this information or access to this information through a wide array of different connections through maybe different Active Directory groups and things of that nature. But you won't know exactly the number of connections or how they're connected at the time you're originally looking at the query. All you know is you want to find out how two people or two entities are related inside this. So this is really sort of, when I think about graphs and graph type problems, these are the sorts of problems I really look for, where graphs benefit the end use case quite significantly. And why is this? Well, there's a few challenges around using many other technologies with highly connected data. First, they tend to be a little unnatural for querying that data. And this tends to lead to inefficient processing of that sort of information. And most other databases out there, or other data technologies out there, tend to have a rigid schema that's really inflexible for rapidly changing data that most of the types of use cases we've talked about today, be they fraud graphs or knowledge graphs or security graphs or identity graphs, really tend to require. So let's dive a little bit into that. What is it about graphs that actually make them better to handle this sort of highly connected data? Well, the first aspect here is the query languages. The query languages that we use with graphs are really optimized to use the connections to move through the network of data that you're looking at. And this comes down to the fact that graphs, databases, and managed graph services are based on graph theory. And one of the kind of key pieces of graph theory is this concept of traversing your data, or moving from point A to point B. So if we looked at this specific example, we're looking at this and it says Dave works at Amazon. The little gremlin guy is sort of representing, that's the logo for the Apache Tinkerpop Gremlin project. And that's representing kind of where we are in our information today. When I write queries in graph query languages, as opposed to kind of, the way we work with them, we'll see an example of this later. It really they really work by moving data from point A to point B. So I'm moving through my graph or my network from Dave to Amazon. If we want to contrast this with something like a relational database, relational databases work on relational algebra, set algebra, and they work by combining sets of data. So if we wanted to kind of look at this in the same example here, I would probably have a table called something like person and a table called something like company. I would perform a join on this in order to get the fact that Dave is a person at a company, that I work at that company through some sort of foreign key between those tables. And the way, at its very core, kind of the way that relational databases work, as opposed to moving from point A to point B in a graph, When I move it from point A to point B, I don't necessarily unless I explicitly ask for it, I don't necessarily maintain the history of everywhere I've been. In relational databases, as I'm joining these tables together, I'm building a bigger and bigger table in memory, in theory, in memory that basically is containing all of the information and all of the history of where I've been. This is why when you start running large queries that have to traverse or move through a lot of data in order to get there, graph databases, because I'm moving point A to point B, as opposed to building them in bigger and bigger in-memory table, are more efficient from a memory perspective and a speed perspective in order to do it. The other aspect there is graph databases are really optimized for processing connected data at the kind of engine level. Because graph databases store not just the entities, but the connections, this really gives them the advantage of the fact that the connections that you're working on are data itself. This means that they're physically saved to disk. So when I need to actually retrieve this data in order to know I want to move from point A to point B across a connection, I'm really just reading data again. I'm reading data off of disk to retrieve that information. If we contrast this again with something like a relational database, the WorkSac connection in this example is really metadata. It would be represented through something like a foreign key between that person and company table. So when I want to find out what company somebody works at, I need to actually calculate that at runtime. I need to run that relational algebra to calculate that, as opposed to being able to retrieve it from disk. So when I start needing to process hundreds or thousands or hundreds of thousands or millions or billions of these sorts of relationships, the fact that I can retrieve them from disk versus calculate them at runtime really does lead to a much more efficient processing of that sort of information. And the last kind of item I wanted to touch on here is a little bit about schema flexibility. When we're looking at these two examples up here, we see that we have, these are both representations of family trees. With a graph, and with Amazon Neptune and with most graphs, they're what's known as a schemaless database. I personally, not my favorite terminology, because if you have data, you have schema. So I like to think of it more in terms of explicit versus implicit schema. So in the case of a graph, when I start with its schemaless nature or its implicit nature of schema, I can just start writing information to my system. I can write a person, and I can start writing a property of a first name or a last name. I don't have to declare these ahead of time. I don't have to set up tables or keys or constraints around that. I can just start writing that information to my system as the data that's coming in, or maybe the attributes of that data changes, or we add new. Maybe we add a new type of data, a new set of entities to my graph. I can just start writing those, and they will be automatically included into the schema of my graph. This provides a lot of flexibility, especially as data evolves over time. If we want to compare that and contrast that a little bit to a relational database, relational databases have explicit schema. I needed to declare ahead of time that I have an individual, and that individual has a first and a last name. You do this in pretty much any relational database today. And this is very powerful until you want to start evolving this at scale and speed, where you have to, every time you go and do this, you're going to have to run some sort of, schema migration or schema diff process in order to basically bring things up to speed, versus being able to just start writing the new entities as they come in. There's also a bonus here, which is the fact that graphs tend to be easier to understand by new people or non-technical people that are familiar maybe with the domain. And this is because when we look at these representations, the representation of the graph is a lot more natural to the way we already are looking at the domain than necessarily looking at some ERD diagram that you have to kind of dissect and put back together in order to figure out how everything's going to be related between them. So it's a little bit about graphs and why graphs are better for some sorts of problems than other technologies. But why is it customers come to us, and why do they want to use a graph database service? As we kind of mentioned, traditional database technologies out there really aren't built to scale when you want to do like deep link querying or deep link analysis across billions of interconnected entities, either hundreds of thousands, millions, or billions of interconnected entities for that matter. And because of this, it really challenges those sorts of engines to deliver the low latency required for real-time inspection of things like fraudulent, looking for things like fraudulent activity or personalized recommendations or other potential malicious activities or things like that. Self-managed solutions also tend to be complex expensive and inflexible, especially if you want to try and optimize them and scale them to the global nature of many of today's applications. They require a lot of hardware management, provisioning. You have to manually scale up and down these sorts of items, and being able to do this in a compliant way as schema changes and evolves over time is very complex. And this really leads to a lot of these solutions not being able to evolve at the speed and scale that the landscape of today's data is changing. And this is really why we went and built Amazon Neptune. Amazon Neptune is a fully managed, purpose-built graph database built for the cloud. It was released in May of 2018. And since then, we have been continuously improving it with new features and functionality based on feedback from customers. As I said, it's a fully managed service, so AWS takes care of all the hardware management. We manage the OS, the database server, and we manage all of this through we manage all of this through a couple of ways. All it takes is you as a user a few clicks in the management console or a few calls to the API to provision a new Neptune cluster, and it'll be up and running in a matter of minutes. One of the core needs of any of these sorts of systems is the ability to scale based on demand. So it's critical for most businesses to be able to support burst, traffic that fluctuates over time. Maybe it's seasonal traffic built to burst on Black Friday or Thanksgiving. Maybe it's something, maybe your application gets more traffic in the evening versus the day, and being able to dynamically scale is kind of a critical aspect of the way we built Neptune from the get-go. And the last aspect here I wanted to kind of talk about is cost reduction. In many other database offerings, because they don't scale very linearly, you tend to over provision hardware and database servers and CPUs and things like that to meet your peak demands. Because of the scalable nature of Neptune, we really allow you to reduce the cost to reduce the cost overall and add a lot more predictability to your cost by being able to fluctuate your hardware that you're running your database on up and down as demand happens. Neptune uses a pay-as-you-go model, so you're going to only pay for the amount of time your database server is actually running. So this helps reduce costs further by not over provisioning, overspending, and underutilizing this. As we mentioned, Neptune at its very core is a purpose-built graph database that's optimized to store and map billions of relationships between entities. It does this to enable real-time connections with millisecond query response times. And it does this through support for the 3 open standard query languages, open specification or open standard query languages, those being OpenCypher, Gremlin, and Sparkle. Does this through by supporting the 2 leading graph models out there. The first graph model out there is property graph. Property graph at its very core represents data through the use of nodes representing real-world entities, edges representing connections between those real-world entities, and attributes representing properties of either a node or an edge. And I think that's kind of a key piece to add in there. One of the unique aspects of property graphs is the ability to associate properties not only with the entities themselves, as you can with many other database technologies, but also the ability to associate those properties specifically with the connection between entities. So maybe you have a person and maybe they have a product, and you have an edge that says maybe they were bought. Well, you can also store, besides just saying the fact that, A bought product B, you can also add properties or metadata to that edge. Maybe you want to add where how they bought it to, or the date they bought that as a property of that connection itself. So it's kind of a unique aspect of property graphs. If you choose the property graph model in Neptune, you have the ability to query that data through one of 2 open specification query languages. One of those being OpenCypher query language, which is provides a SQL-inspired syntax for customers to use. The second being the Apache Tinkerpop Gremlin query language, which is a very powerful query language that we'll look at both of these here in a little bit, but look and compare them. But Gremlin is a very almost stream processing oriented query type language. The second graph model that we store in Neptune, or that you can choose to use in Neptune, is the Resource Description Framework, or RDF. You might have heard this referred to as the semantic web construct, but RDF represents data inside a graph as a set of triples. Each of those triples containing a subject, a predicate, and an object. So if we go back to the earlier example of Dave works at Amazon, if we wanted to look at this with an RDF data model, we would represent that data as the subject would be Dave, the object would be works at, and the predicate would be Amazon. If you choose to use the RDF data model inside Neptune, we support querying that data using Sparkle 1.1, which is a W3C standard query language for querying RDF data. We have thousands of customers are using Neptune today in production. This is just kind of a really quick, short list of some of our Neptune customers across different verticals and different use cases. So, what is Neptune? How does Neptune work? Let's take a moment and look under the hood of Neptune and how Neptune is built, what its architecture looks like, and then talk a little bit about some of the features and functionality of Neptune. So when I think about Neptune at the high level, I think the architecture, when I think about the architecture of Neptune, I sort of think of it in these sort of 5 basic areas: the application layer, the compute layer, the shared storage layer, a set of service features, and service integrations. One of the unique aspects of the general architecture of Neptune is that we were, with Neptune, we were able to break out the compute layer from the shared storage layer. It's kind of a very key piece of the architecture. And this really enables us to provide a lot of these features that your applications work. So let's dive in and take a little bit of look and take a moment to look at some of these. The first layer here we wanted to talk about is that application layer. This is where you as the developer really live and work. This is where you're building your social networking application or your fraud detection application. Maybe it's a knowledge graph or a security graph or one of the other use cases we talked about. But this is where you're interacting with it. And you do this through any of our 3 query languages, as we mentioned. And this basically is for property graph, we basically have a set of endpoints exposed both via HTTP or a WebSocket or bolt connection. If you're using property graphs, to be able to write that data to and from the system. So you're using a set of open source drivers or open drivers or REST API end calls to interact with this system. This system, these applications are going to interact with this compute layer. As I mentioned, the compute layer in Neptune is separated out from the storage layer in a kind of a unique way for cloud data or bases, or cloud-based graph database, excuse me. And the compute instances are built to allow you to scale dynamically scale as your application requires. It's a instance-based database, so your compute layers can have up to 16 different instances. There's always one writer instance or one primary instance. That primary instance can be scaled anywhere from our smallest being a T3 medium up to an R5 24XL, or recently we also, if you have a high memory demands on your application, we also recently released support for the X2G family of lines. So you can scale that writer up from to any of the sizes available within there in a vertical manner. For reads, most graph applications tend to be very read heavy. So we allow you to scale out to up to 15 different read replicas on top of that same data. You're storing that data one time. Each of these read replicas basically will read that same data. And those read replicas allow you to scale yet again, also vertically from a T3 medium all the way up to an R4 24XL or X2Gs, as well as scale horizontally. So from an instance perspective, the write instances can scale vertically and the read instances can scale both horizontally and vertically. All of this compute instance is separated out from our shared storage layer. We'll jump into a lot more of the details about this in a few minutes. But at a high level, this is a strong feature of the cloud native aspect of Neptune is this shared storage layer that's separated from the compute layer. When you write data into Neptune, that data is automatically going to be stored 6 times, twice in each of 3 availability zones. The data scales independent of your compute, but it scales automatically for you. So when you start a Neptune cluster, it'll start with provision space for 10 gigabytes of data. And it will, as you add more and more data, that provision space will grow up to 128 terabytes. Because it's a fully managed service, we have a lot of features around automated backup and restore functionality for you. And we have this ability, we call it the database fast clone, which is really about enabling you as a user to quickly make a copy of your database to maybe do something like try out a new engine version or to try something in your application without having to take down your production cluster in order to make this happen. Neptune also comes with a set of service features that are part of the actual native implementation itself. The first one being the ability to bulk load. If you're going to bulk load data into Neptune, we provide an endpoint inside of the system that allows you to trigger this bulk load from S3 files. The S3 files have to be in one of a few sets of specified formats. If you're doing property graph, there's 2 different CSV formats you can use. If you're doing RDF, there is 3 different RDF data formats you can use. Once your data is formatted into that, you trigger this bulk load. This bulk load then reads in all of that data, optimizes and parallelizes the load to give you the maximum performance for getting that bulk data into your system. We also have Neptune Streams. Neptune Streams is a CDC type functionality on top of Neptune that enables you to basically get a continuous data stream or a continuous stream of data data changes that are happening inside of your graph. This can be used to trigger some sort of downstream workflows or to be able to basically propagate those changes to other external systems. We also have a status endpoint on the cluster. This cluster status endpoint basically tells you just basic information about the health of your cluster. We have a query profiling and explaining endpoints that allow you to take Sparkle, Gremlin, or OpenCypher queries, run them through these, and get a very detailed look about how the engine is processing that data. This allows you to then go a step further and be able to tune and optimize those queries based on the information being returned to you from those endpoints. We also have a feature that allows you to auto-scale read replicas. We'll talk a bit about this in a moment, but this basically, at a high level, this feature enables you as the user to specify a set of thresholds at which point your cluster will scale up and down to match the workload demands based on those thresholds. Neptune also comes with a few sets of service integrations. The first service integration is an integration with the AWS backup service. So if you're an enterprise or you're in your account, you use AWS backup, you can now back up that data, or you can now back up your Neptune data using that same service. We also have a feature called Neptune ML. We'll talk a bit about that here in a moment. But at a high level, what Neptune ML is it's an integration between Neptune and SageMaker to enable customers of the Neptune Graph database to build and automate the process of building graph neural network-based machine learning models and using those models to run real-time predictions inside of queries. We also have an integration with Amazon OpenSearch. Our integration with Amazon OpenSearch enables you as a user to query OpenSearch for full text search type responses or full text search type queries, and get those data, get that information propagated back into your query itself. As I mentioned, kind of one of the key pieces of the architecture is this cloud native storage layer that we have inside Neptune itself. This is a piece of really battle hardened technology inside Amazon, where when you write data, as I mentioned previously, that data is automatically written in a highly available and secure manner. This data is replicated 6 times, as I said, 2 times in each of 3 availability zones. It's also continuously backed up to Amazon S3. This storage layer itself was built for 11 nines of durability, and it's based on this basically 10 gigabyte segment sizes. This 10 gigabyte segment size, as I said, when you start a cluster, you get one 10 gigabyte data size or data segment. As you add more and more data to your cluster, we automatically provision these additional data segments for you. And this data segment is really the unit of repair that this system automatically uses to heal itself and to rebalance hotspots inside of the storage layer, things like that. A quorum system is used for reads and writes, so it's very latency tolerant. And as I mentioned, this storage volume will automatically grow up to 128 different terabytes. Up to 128 terabytes. Read replicas. Read replicas, beyond just scaling scaling the number of transactions you can use, there's a couple of really key aspects about read replicas. As I mentioned, Neptune is an instance-based database, and you can run it with as few as a single instance, in which case that instance will be a writer. When you're doing if you're running in something like a single instance node, with only a single instance, excuse me, if there's something that goes on with that writer node where for some reason that node fails, it will automatically be rebooted by the system, but that can take several minutes to come up. So during that time, you won't be able to serve any traffic inside of your app or any traffic from your cluster to any sort of applications using it. If you set up a read replica, that read replica will basically be used as a failover. So if that primary writer node goes down for some reason, that read replica will be promoted to the writer, and the writer node will be, what was the writer node will be restarted as the read replica itself. And this really, this automatic failure detection and things like that will really minimizes the amount of time that your application won't be able to serve traffic. The other reason customers tend to use a lot of read replicas is to scale out the read traffic. As I mentioned, you can scale out the read traffic across your different, up to 15 different read replicas and balance the read requests and responses based across that using the reader endpoint. So that sort of kind of brings us to how is traffic? How do you work with Neptune? How do you actually read and write data to it? When you work with Neptune, you're basically given, or I should say, when you create a Neptune cluster, you're giving two different endpoints. You're giving a writer endpoint and a reader endpoint. The writer endpoint, also referred to as the cluster endpoint, always points to the current writer, always points to the current primary instance. This is the one you would use to do any sort of mutation queries on top of your data. If you have read-heavy queries, as many applications do, we also provide you a read endpoint. And this read endpoint distributes those requests as they come into different read replicas. So if you have 3 different read replicas, this reader endpoint will round robin distribute requests across this will round robin for a specified period of time will point to different things. So your requests will be distributed across your different instances. That being said, this reader endpoint is time-based. There's no fairness or round robin guarantees, but this is often sufficient for many customers. One point to note here is if you're using Gremlin with their WebSockets or using the OC Bolt connections, those connections once created are sticky, so they'll stick to a specific read replica. So it's something to be aware of, that you may end up with hotspots in your applications if you are using WebSockets or Bolt. Customers also can build custom request distribution strategies. We've had customers that have built them around fairness or to optimize cache locality. These have to be done at the application level if you want to do this if you want to build these sorts of custom distribution strategies. And you also need to be aware of potential failover scenarios and how you are going to handle that. Another key aspect of the Neptune architecture is caching. Within Neptune, there's 3 different types of cache that are used. The first being a buffer cache. This is always on. As soon as you spin up any instance, this buffer cache is enabled, and it's used to store pages of data, of graph data from that shared storage layer in local memory. This really enables much faster queries by being able to pull frequently used data from the local instance memory, as opposed to having to go across and fetch that from the actual storage layer itself. As I said, this is always on. It's enabled by default. There's nothing you as the user needs to do here. One thing I would recommend is to monitor there's a CloudWatch metric called buffer cache hit ratio, and you really want to make sure that's up in the high 90%. And you can use that by monitoring that, or you can figure that out by monitoring that metric inside CloudWatch. The second type of cache we have is an optional cache. It's a lookup cache. This only works if this lookup cache, I should say, is only available if you have R5D instances, because what it's doing is it's using the NVMe based SSD SSD disks to store property values and literals for use cases where you're frequently returning large numbers of these property values to users. This is something you can set up on a per instance basis and will automatically be used. be used when to store that data. That data will automatically be populated into those NVMe disks as it's being used. The second one is the query results cache. The query results cache uses the instance memory. It's also an optional opt-in cache. And it's exactly what you expect it to be. It stores the query results. So on a per query basis, you can specify that you want to use this query results cache to store that data into, to cache those query results for a specified amount of time. This is really used for cases where you have maybe the same query is highly repeated, but the data being returned doesn't change. The other and probably most common use case we've seen with customers is for pagination. If you want to be able to run a query one time that basically goes out, pulls a lot of data, orders it, and returns the first 10 results, and then you want to page to the second 10 results and the third 10 results. This sort of query results cache is really very helpful there, because you will have to, you run that query one time, you can store those cache, you can cache those results for a TTL, and the next time you go to pull the second page, it'll be in very, very quick, a few milliseconds sort of response time to get that back, because you're pulling it directly from this query results cache. Security is also, as with all databases, is a very key aspect of the Neptune architecture. Neptune is built with network isolation. It is a VPC only database. So any applications, or there is no public endpoint, so any applications or users that want to do it have to have access inside that VPC in order to talk to Neptune. Data is encrypted with Neptune. Data is encrypted at rest using AWS's KMS. You can either specify a specific key or use the default key for your application. Encryption is also handled in transit through SSL. From a user perspective, Neptune is integrated with IAM authentication. So you can use IAM policies in order to manage access into your Neptune, or into Neptune. The database, any Neptune cluster can be IAM enabled. So every request to that database will require IAM authentication in order to make it happen. And we have a fine-grained set of action-based access controls to really granularly grant people access to different actions and to different data plane type actions inside the system. As I mentioned, Neptune is a fully managed system, so we have a variety of automated backup and restore functionalities. Daily automated backups will occur during a window that you can specify, in which case the full storage volume snapshot is taken. The retention period on these automated backups can be configured by the customer to be between 1 and 35 days. You can also manually create snapshots of your data to back up an entire database instance. Manual snapshots can also be shared across accounts. So if you have a use case where you need to be able to take a snapshot of your data and move it to maybe a prod account, or from a prod account to a QA account to a test account, things like that, you can do that, and they can be copied across regions. You have not only do we have the ability to take a snapshot, but you can restore those database snapshots to a new database instance. This allows you to also do things like if you want to change the parameter or security groups around it to test out new settings, you can do that. And Neptune also supports point-in-time restore, so you can restore the database instance to any specific time down to a 1-second granularity. Not listed here, I briefly earlier, is also a fast clone capability, which basically quickly allows you to make an entire clone of your database to be able to test out new and different features. Another key aspect is the ability to monitor your cluster as it's running. Neptune integrates with CloudWatch and CloudTrail CloudWatch and CloudTrail services to basically log all the API calls that Neptune makes, as well as look at different metrics around the database. We want to look at the CPU and memory utilization of all of the instances in our system. We can look at things like, what is the query throughput? What are the success and error rates of that? What is my read and write throughput? How much storage is my system using? There's also there's an optional mechanism to enable audit logs. Audit logs will contain a very granular set of information about every query that's been or every query that's being processed by the thing or by the engine. It's going to have information like timestamps, what are the servers and client hosts, what message was sent across, and that's all going to be stored inside of your CloudWatch logs. So it's a little bit about the architecture. Let's talk a little bit about some of the new features and functionality that Neptune has, and then we'll jump into a bit of a deep dive and demo on how that works. One of the newest features we have for Neptune is a Python integration, specifically kind of targeted at running some graph analytics. And what this is an open source Python integration that allows you to easily read and write data stored in Neptune by removing the undifferentiated heavy work of managing connections and working with data or getting data to and from the format that graph query languages return to kind of something that's more usable for most customers. In this case, we've using pandas data frames as sort of the lingua franca between these two. This library basically enables you to read and write data from Neptune and to pull that data into Pythons, where you can use any of the popular open source Python tools out there to do further analysis. So maybe you wanted to run some sort of analytics or algorithm on top of it. You could pull data down using this in the pandas data frame, and then use a network analysis library like iGraph or NetworkX to run some sort of small scale analysis on top of your data. This also comes with a set of sample application notebooks on how you can actually use it. The next feature I wanted to highlight here was released in the spring of 2022 here, and that is our support for OpenCypher. So OpenCypher is a widely adopted open query language for property graphs. It provides an intuitive way to work with property graphs by providing developers, business analysts, or data scientists a SQL-inspired syntax that has a familiar structure that you can use to compose queries for graph applications. This really enables customers that come from a relational background or are familiar with SQL to have a very smooth on-ramp onto working with graph databases. One of the unique aspects of our support for OpenCypher is we have built this in such a way that you can load your property graph data into Neptune once, and then you could use OpenCypher or the Gremlin query language on top of that same data. This really allows customers that either are migrating from other systems or have an application already in Neptune to start getting able to use OpenCypher very easily. Neptune also supports the OpenCypher Bolt protocol, and this basically allows customers that are running current workloads to migrate those workloads to Neptune with a minimal amount of changes to their application. The next feature I wanted to talk about here is Neptune ML. As I alluded to earlier, Neptune ML is an integration between Amazon Neptune and SageMaker to enable graph developers to make machine learning-based predictions on graph data without having a ton of machine learning expertise. It does this by automating a lot of the choices you would need to make in order to build your machine learning model, being which model is the best one to use, what training instance sizes I need, what processing instance sizes, things like that. This is all based on state-of-the-art machine learning techniques, specifically using GNNs or graph neural network-based machine learning techniques. And these have been shown in some external studies to be up to 50% more accurate than some other machine learning-based models, machine learning-based paradigms out there. Neptune ML is really built to scale to the large data sets that we have our customers of Neptune using today, because when you're working with knowledge graphs or fraud detection or product recommendations, you're talking about extremely large amounts of entities you're working at, maybe up to billions of relationships. Neptune ML went GA about a year ago, and recently we have added support for custom models, which allows customers that have expertise already in GNNs to build their own custom model implementations of Python, but still be able to use that with the rest of the Neptune ML framework. And we added support for Sparkle. So now you can, whether you're using Property Graph or you're using RDF, you can use Neptune ML to enable machine learning-based predictions on that graph data. We also recently announced fine-grained access control for data plane actions. This is really about allowing the customers to specify at a very granular level which sort of actions a specific IAM role can take. So this allows you to specify roles that are maybe only have access to read, or only have access to write, or only have access to trigger bulk loads, things of that nature. This really allows for kind of least privileged access, allows you to set up least privileged access for applications that are using Neptune to give them only the specific permissions that they need. This is now the default when you turn on IAM authentication as of the 1.2.0.0 release. And it really allows you to create those separate policies to any data plane API. Another feature we recently added to simplify some of the operational headaches is the auto-scaling read replicas. As we talked about earlier, Neptune is an instance-based database. It allows you to scale read replicas up to 15 of them. And auto-scaling read replicas allows you to specify a minimum and a maximum capacity for that, a scaling threshold based on some of the CloudWatch metrics, and then it will automate the scaling activities as your workload demands. So as your workload ramps up, it will scale out additional read replicas. As your workload demand eases, it will scale those back. So it really helps automate the process of doing that, as well as provide you some cost optimization by not having to run additional read replicas when they're not needed. Another operational simplicity that feature that we recently released is one I'm very excited about, and that's Neptune Global Databases. Neptune Global Databases allows you to deploy Neptune clusters across multiple AWS regions for fast cross-region disaster recovery or low latency queries. The two reasons, at its core, Neptune Global Databases allows you to set up one primary cluster in up to 5 different secondary clusters that are read-only in different AWS regions. Two main reasons we've talked with customers are interested in this feature. The first is disaster recovery. In a scenario where you may have a regional outage, customers want to be able to easily have their data, easily maintain business continuity of their data when a region's out by failing over to another region. The second common use case we have talked with customers about is for global applications, being able to co-locate your data closer to where your user is to now enable lower latency reads as part of a kind of a global data distribution strategy. This is, as I mentioned, this is a managed feature. So there's, it would allow for things like fast cross-region migrations. And it's got a low replica lag between these regions. So the data is going to automatically be written into the primary region, and then that will be automatically replicated out with a low latency to the other AWS regions that you have clusters configured for. Beyond just new features and optimizations for operations, we actually have several new features related to cost optimization for users of our system. First being our support for Graviton 2. Graviton 2 in our testing has shown to improve query latency and lower the cost compared to some x86 instance sizes. So not only do you get faster queries, you get to pay less for them. So that's always a real benefit to customers. And this is partially, there's a lot of reasons behind this, but part of this is also we inherit some of the benefits of the AWS Nitro system for private networking and fast local storage. As of today, we support the T4G series for low cost development and test type workloads. We also support the R6G series, and recently we added support for the X2G series for any sorts of use cases where being able to have a lot of memory or a lot of buffer cache is beneficial. As of April, we also now offer a free trial offer for Neptune. This free trial offer does not limit the features of Neptune. This means if you're in an organization that has not created a Neptune cluster, you can get started using this or trying out Neptune for free. And this means you can use any of our 2 graph models or 3 query languages to do it. For eligible customers, you're going to get up to 750 hours of T3 medium instances, 10 million IOs, a gigabyte of storage, a gigabyte of backup, and this is going to be free for 30 days with no restrictions. After the 30 days, it's going to revert to a pay-as-you-go model, so you're only going to pay for the resources you consumed, no upfront licensing costs. So now that we're kind of walk through a bit about what graphs are, what is Amazon Neptune, some of the features of it, let's do a deep dive and demo and take a look about how you can set up a Neptune cluster and then why you might want to use this with for some of the common use cases we discussed. So what we're looking at here is we're looking at the Neptune console. What I'm going to walk through is, if you're coming in here, you're new to Neptune and you want to create a database, let's take a look at what you need to do in order to make that happen. We're going to start here. We're going to click on Create Database. It's going to provide you a list of options. You can specify the version that you want to have of Neptune. Especially if you're testing it out, I almost always recommend you try out the newest version of the system. You can specify a specific identifier for this. In this case, it defaults to a name of database 1. You can also specify the template. And the template here basically lets you choose or specifies the set of instance sizes and some basic configuration parameters that you have. When you select the dev and test instance, it provides you access to the T3 medium burstable class of instances. These are really only good for development and testing type scenarios. So if you want to create a production type cluster, you want to select the production template, which is what I'm going to do here. From there, I can select the instance sizes I have. As you can see, we have quite a few instance sizes to choose from. I'm just going to leave it at the default one right now of R6G extra large. You can also, in a production, when you select the production template, you also get the option to create a read replica in a different availability zone right out of the box. You can specify if you have very specific VPCs you want it in, you can specify that sort of things. We also have the ability to create a notebook. Didn't mention this until now, but one of the features that comes with Neptune is this construct of a Neptune notebook. A Neptune notebook is a free open source package. We'll see it here in just a moment. And it runs on top of the Jupyter web-based IDE and provides the ability to run things, to be able to interact with your cluster as sort of the IDE for Neptune. So we can automatically create one here. I already have a database up, so I'm not going to do it here. But if I clicked Create Database, at this point, what would go through is it would go in, it would provision out that storage, it would provision out the instances you had, and it would spin all of this up. And within a few minutes, you would end up with a database that shows up here. It would show up as available. In this case, as you can see, I have two databases, two clusters, excuse me. One called Air Routes, one's called Altimeter. They both have a single writer instance, and they're both currently available. So let's jump in to one of these and start taking a look at what it looks like to actually work and interact with Neptune. As I mentioned, we're going to be using what is known as the Neptune notebooks. This is a Jupyter notebook, so this is a free open source package. If I come in here to notebooks, you can see I have one notebook running. I can open it from there. This IDE is exactly, this is the IDE we provide into Neptune. It's you can run this either as a hosted piece of infrastructure or not. As you can see, when I click on this, it pops up a hosted Jupyter notebook. This is hosted as part of SageMaker Notebooks. You can either use this open source Neptune Notebooks package through these hosted instances, as I am here, or if you have your own Jupyter server, you can run and install this. And as long as you have connectivity into your Neptune, the VPC where Neptune exists, you'll be able to run these sorts of things. When we come in here, we'll see there's a set of notebooks in here automatically. We have ones around a few getting started notebooks that really go into talking about what is a little bit about Neptune notebooks, how you can use that to access the graphs, a few different examples. We have some example notebooks that go through the different types of visualizations that you can actually build and run with Neptune notebooks. We'll see those here in a moment. We also have some sample applications specifically around fraud graphs, knowledge graphs, and identity graphs that enable you to be able to go in and give you a set of predefined, gives a set of predefined data that you can load into your cluster, as well as a set of predefined queries that you can start to see how you might go about building one of these sorts of use case applications. And we have a set on machine learning. If you're interested in using Neptune ML, you can come in here, look at the Neptune, this 04 machine learning, and this will give you a very detailed walkthrough of the different features and functionality of that feature of Neptune. For this example, I'm going to jump into this notebook that I have called OC Gremlin examples, and let's take a little bit of a look at what some of the things we can do here. As I mentioned, we have that query, we have that status endpoint on our cluster. With Neptune, one of the things, with Neptune notebooks, it provides a set of what are known in Jupyter as magics. Anything that starts with this % sign is one of those, is a magic. And it basically allows you to do a specific feature and a piece of functionality here. In this case, this status one is going out, querying that endpoint, that status endpoint, and bringing back the data. So you can see the different types of information here. You can see when my cluster was started, what's the role of it, what's the engine version I'm working on, what versions of Gremlin, Sparkle, and OpenCypher are supported, any of the lab mode or beta features I'm looking at here, any of the other features such as the result cache that I may have enabled. Beyond that, we can also do things in our cluster like bulk load data. So if you have data stored in an S3 bucket, you can use Neptune notebooks to kind of give you a graphical walkthrough of being able to set up that the call that basically triggers that sort of thing. I'm not going to do that here. We also have a fast reset functionality. So if you're in the stage of building your application where you need to be able to clear out your database quickly, you can use the fast reset, or in this case, through the DB reset widget, to be able to basically wipe all the data out of your cluster and start over from scratch. I'm not going to do that here because I have some data loaded in here. The other command that's very useful here is, as I mentioned, we have some seed data sets, some data sets for very specific types of use cases that we provide out to the user through this notebook that you can use to get started here. And what we're going to use here is, I've already loaded this data, but one of these is a set of air routes data. So this is airports and flights between airports. And we're going to use that to kind of walk through a little bit about what going and querying these graphs sort of look like. So in this case, we're going to be working with property graphs. And I'm going to be showing talking a little bit about some of the basics of graph query languages and how you can use those to do things. The first one we're looking at here is OpenCypher. OpenCypher is, as we mentioned, has a SQL-inspired syntax. So if you're looking at this, you can probably right away, even without me telling you anything, probably have a reasonably good idea of what's going on here. In this case, OpenCypher is based on kind of a pattern matching syntax. Anywhere you see the parentheses, that represents a node. We'll see it here in a minute, but anywhere that you see kind of an arrow and a line represents connections, and you can use this to build more complex types of queries. In this case, it's kind of the most basic query you can look for. I'm just going to be looking, I want to match any nodes. That node's going to be labeled N, and I want to match any nodes where the code of the airport is ANC for Anchorage Airport. I can come in here, I can run this. You'll see it'll give me back basically the information I had. I can view this in the JSON format that's natively returned from Neptune. I can also view this as a graph. This is one of kind of the key features of Neptune notebooks, is this ability to come in here, and I'll make this bigger. We can come in here, look at this thing. In this case, it's not as interesting as it would be in some other cases because it's just a single entity, but I can come in here. I can also look at all of the properties that were returned as associated here. So we can see these are the, this is that property graph model where you're looking at nodes, the node in this case being an airport, as well as the attributes associated with, or properties associated with it. The other live query language we support for property graphs is Gremlin. As I mentioned, compared to the SQL-inspired syntax of OpenCypher, Gremlin is more of a stream processing type language, where data is pulled in from kind of one side of a step, some aspect or process is done on it, and it's sent on to the next one. So in this case, I'm saying G is just a convention for kind of starting with a graph. In this case, you can sort of read this query as starting with a graph. I want to find all of my vertices. And then I want to filter this down to only having ones where the code for the property code matches ANC, excuse me, for the Anchorage Airport. And then element map basically says, bring me back all of the properties associated with that. If I go in and I run this, we'll see I get back a very similar, I get back the similar set of information. The formatting's different between them. But I can also view this one as a graph as well. So this is the sort of pieces and functionality there. Let's kind of, that's a very basic way to use both the Neptune notebooks as well as OC. Let's take a little bit, a little bit of a more interesting look at some of the more complex things. Let's start using some of that pattern-based syntax. So in this case, not only am I starting at the location of the Anchorage Airport, I have added this additional functionality with these dashes and these squares to basically say, I want to now traverse out from this Anchorage Airport. I want to traverse out any edges that are specified as a route to a destination airport. So basically, I want to find anywhere I can fly to or from Anchorage. I go and I run this. We see that comes back very quickly. And I'm able to graph this out in such a way that I can see basically, I can see all of the airports that are connected into the Anchorage Airport itself. If I wanted, yet again, I could come in here and start going through and looking at different properties associated with these items, as well as properties associated with the edges. As I mentioned earlier, edges can have properties inside of edges can have attributes representing properties of those edges. In this case, I have this property called dist, which represents the distance that I need to fly in order to get there. This is very powerful to be able to create these sorts of patterns that work to filter very efficiently and effectively. I'm not going to go through all of the examples here with Gremlin, exactly what's going on, but these are, I'm able to run the same sort of queries in both OpenCypher, Gremlin, get back answers that are the same sort of answers. Going to jump next into one of the things Din mentioned about property graphs is when I'm creating relationships inside of a property graph, those relationships have directions associated with them. There's a directionality aspect to it. You have this relationship is going from someplace to someplace. You can represent that inside of your graph query languages. In the case of OpenCypher, you represent this using arrowheads, kind of pointing in the direction that you're looking for. So in this case, as opposed to finding all of the airports that I could fly to or from Anchorage I am now only finding the places I can fly from Anchorage to. So Anchorage is going to be my start location, and these are the airports I can fly to. We can represent the same thing inside of Gremlin using a different set of steps that specifies the directionality here. But the key piece to note here is, edges inside graphs have directions, and you can use that directionality as a filtering criteria. You can sort of think about this if you want to think about it from the construct of like something like a social network. If you're on Twitter, you might follow somebody, but that person may not follow you back, something like that. So using that directionality as an aspect of your data modeling is kind of a really strong feature of graph databases. And you can keep extending this out. You can extend this out. In this case, I'm not just finding everywhere I can fly to, but I'm finding everywhere that I can fly to from Anchorage that I can then fly to Austin. So basically, I can want to find, in this case, 2 hops. I'm specifying the exact number of hops. So if you want to think yet again in a social network sort of sense, this is like the friends of my friends sort of idea. But when it really comes down to it, these, even these sorts of queries are ones that other databases can probably handle. You could probably write a query inside of SQL. You've probably written similar queries where you'd be able to join tables together multiple times. Really, the power of graph query language starts to happen when you have these variable length queries. And these are represented naturally inside both Gremlin and the OpenCypher query language has really native constructs of the language to support this sort of thing. So in this case, I want to, in this case, my query is finding all of the flights from Anchorage to Sydney that are within 4 hops. So this is where this, this variable length query syntax starts in. In the case of OpenCypher, you do this using this star 1.4 in this example. and it's going to find me I put a limit on this because otherwise it's going to return quite a lot of data. But this is going to, you can start to see how you can use this to very quickly and efficiently find these sorts of variable length connections that in ways that if you were going to do this in other technologies, you'd have to write like recursive functions or some sort of CTE, common table expression, in order to be able to return it. As I mentioned, this is supported both natively in OpenCypher or inside of the Gremlin query language here. So that's a little bit of kind of the basics of graph query languages, how you sort of write these. Let's jump right in and maybe take a moment to actually look at what this looks like for a real use case. And in this case, we're going to look at security graphs. We're going to look at a security graph use case and why you might want to use a graph to do this. And we're going to do this by graphing our AWS resources. We're all sitting here working on top of AWS. Let's take a look at what our resources look like and what it looks like as a graph. Your resources in AWS kind of are naturally lend themselves to graph representations because there's a lot of connections between these items, and these connections are really, in many cases, the key things that you want to look at. Let's start by just taking a look. Let's see if we have any policies out there that are potentially insecure. Maybe these are anywhere where you have an administrator, the administrator access policy, or you have created any policies where you have a star as part of the document text. We can sit there and basically take a look very quickly and see that we have two of these policies out there. We have an administrator access policy, as does everybody. Also, somebody has created this policy called OpenS3. Not sure why somebody decided that we should, create an OpenS3 policy, but we should probably investigate that a bit further and see exactly how that's being used. The first part here is let's take a role. Let's take a moment and see if there are any roles using this, because you might have the policy, but if it's not being used, it may not be a big deal. If we take a look at this, we can see that we have, a few different roles be using this. We have this role called altimeter that's using both this OpenS3 policy as well as the administrator policy. So we're going to probably want to take a moment and dive a little bit more deeper into some of these, how these are being used to see if we have any potential security issues. So, let's jump to the next step and basically say, okay, we have these roles, we have these access. What resources inside my system are actually using it? So what we can see is that there's an EC2 instance that is using this OpenS3 role. We can also come in here and see that there's another EC2 instance that's using this I need admin access role. Probably, do they really need admin access? I don't know. We probably need to do a bit further investigation into that as well and take a look at what's going on there. So what all connects to these resources? As we can see, we're starting to build out kind of a much more robust query to basically find everything, all these policies. Now we're finding roles. Now we're looking at all of the things that are connected to this, and we can kind of see that we're really building upon this query in an iterative nature. And we're using that to start to see more and more information and data about our system based on the connections and the connectivity of these systems. We can start to see there's a lot of things connected to this. There's a lot of different VPNs and internet gateways. Looks like there's a database connected to this over here. So this fact that we have these very permissive policies is something we probably want to take a look at from a security perspective inside of our own system here. You can then take this and build it out further and further. And this, and as you're doing this, you can also filter it down to being able to only show things that are more interesting to the specific question you're trying to answer. For example, I don't necessarily need to look at the VPCs associated with this because I'm really more interested in what EC2 instances are using these very permissive policies and roles inside of my AWS architecture. And then finally, I want to be able to, potentially look at potential security or threat vectors associated with this. I want to see not just that these EC2 instances are using these roles, but are any of these actually exposed to the internet? And in this case, as we can kind of see, both of these are actually exposed to the internet as well. So we would definitely want to go look at locking these sorts of things down to be able to find, to be able to make sure that we're securing our infrastructure appropriately. So this is just kind of a quick use case or a quick example of how you might want to use, a real world type of use case for a security graph on top of the Amazon Neptune graph database. If you're interested in trying out that demo yourself, we have a couple of resources for you to start with. The tool that I use to map out all of my AWS infrastructure is an open source project from Tableau called Altimeter, And it, under the cover, what it does is it goes out with sufficient permissions. It goes and reads the different configurations of your AWS resources and generates a graph, which can be stored in Amazon Neptune. If you're interested in how to do this, the second link I have there actually is a blog post on how to exactly do that on top of Neptune, how to install it correctly, how to make it, and then how to work with it inside of Neptune. So as we're kind of wrapping up here, I wanted to give you a few additional resources on how you can kind of get started with using Neptune. First, the first link you see up here is the link to the Neptune notebooks or the Graph Notebook project, the one that I used for this demo that provides that IDE type application or the IDE interface for Neptune. If you're interested in how you can use Neptune, what some reference architectures are for it, you can follow the second link here. We also have a set of full stack or a set of applications from full stack applications to partial applications, sample applications that the third link here will show. And lastly, if you're just interested in how other customers are using this, what blogs we have, code samples, videos, you can use the last link here will take you to those areas specifically for Amazon Neptune. Thank you for listening to me today. Once again, my name is Dave Beckberger, and you can find me on Twitter at BACHBD. Thank you.